We are live. Hey Jordi. What? Konnichiwa? Subete? What, what does what does that mean? Subete. All weird. The two of us, Jordi. Nobody else showed up. Too good of a weather today. Hey, Rohan, you're there. Hello, hello. So, oh, the sheeple. I guess you people are getting some tea because you never would expect that I'm on time. Here we are. Yeah, it's a little bit cold. Too much. Johnny sent. Hey, Casper. Hey, Sonic. Uh, Johnny sending too cold, too late for tea. Do you stay awake? I had. I don't know why I feel tired. I mean, I was swimming a kilometer today, but uh, that went well. Um, it wasn't exhausting at all, and I slept for 9 hours and still I'm tired. I don't know why. Must be some parasite or something. Too much boost. No, I had no boost at all since 1 week. I didn't have. Maybe that's the problem. Lack of booster. Ma, ma rest harder. Yeah. In the morning I woke up and it was I felt like groggy, and I opened the window because we had like, I don't know, fresh air. It was quite hot in this sleeping room, so I let in some air and then slept for another 3 hours. So hey Johnny, here you are. We were just talking about the cold air that you sending over from the north to the Central Europe. Hey Ricky. Yeah, the sheeple is quite. The sheeple wants to be 110 years old, and I am too, but I'm not as healthy as the sheeple are. Hey Yombo, oh, no, everyone arrives now. You're curious about everything. Hey Bepstein, nice. Thank you very much. I already feel like 110 years old. Yeah, then we will need to wait until you feel like 120 years old. Bepstein is your last name. Okay. Health, health issues. Yeah. Yeah, back pain. Back pain is my constant um, partner. So I hope Basil shows up, because Basil was quite helpful figuring out a few things about no, this thing here. Oh, maybe I should get the camera closer. Ah! Let's get it closer. Feels like I'm pulling some cables here. Okay, so yeah, I saw that new board with the connectors on the other side, even though the markings are on this side. Back problems. All right, so should I turn it on? Look at this. One connector is for these here, the row controllers and the main controller. I think it's this one here. Then we have this one is for all the little MCUs. We have some jumpers. We can like 4 columns we can deactivate at a time. And then we have the LED power. Lots of MCUs. Yeah, it's only 512. That's one of the boards. Yeah, so I made this adapter here for holding the board in place because that was quite jiggly. Um, all in Blender, of course. I will show you the programming jig there. That worked. Yeah, it was second attempt, I must admit. The first one, not only I had like the hole was not like shifted 2 millimeters, but also the print failed. Yeah, Progabot. That's a quite cool thing. I will show you how that works. Okay, here it is. It turned out different than I expected. So I have the frame. So there is the Linky. It's just USB cable attached to the PTFE tubes for the filament. Then we have a frame which has I don't know if you can see that. Hey IDT. There are like teeth which basically locks on the chips. Then this is the holder with pogo pins, three pogo pins. So there are different configurations. Unfortunately, I wasn't like very good with planning of the PCB. I can show you with this empty PCB here. So, but this doesn't lock in. So usually that will just be more or less fixed. I will just use some tape and I will show you how that turns out. So I can either use my MQTT controls here. Let's turn it on. Here, there is, oops, wrong. Here. Oops. Can I reset that? Here we go. Okay, we will watch the bot moving. Yeah, I can use the dashboard. Oh, let's zoom in. Okay, that's 1 centimeter, and this is just hovering. I will just get closer so you can see. This is just hovering above the pads. I think there is a slight shift. Wait. Focus. Yeah, we can move like 0.2. Yes, I'm using the MQTT server. I think this is all right. So, but I'm not really programming right now. So now it's hovering like 1 millimeter above the PCB. We need like at least a millimeter because it bends. Yeah, and then I just run the script. Let me show that PyProgrammer. This is just the script. It just does a row. I would need like to add. Oh yeah, it won't respond, so it will probably just adjust the position several times to try to program it. So I added that. So there is like an offset. It just goes through the offset list just to adjust because there might be some shift because the board is slightly moved. You can't, like, the pads are only 1 millimeter. You not always hit the target. So I have added it, and if I just run that, it will just yeah, it tries. Yeah, and it had the problem not finding the JTAG, so it tries again. just moving it slightly in all directions until it's programmed it successfully. Of course, it won't find anything because this is not the actual board. I added, yeah, here flash failed. I added, and it will just move on. Yeah, this is cool. Isn't that amazing? It tries to adjust the position, but I must admit it tries 5 times, and then if it doesn't succeed, it just moves on. Oh, that's cool, isn't that? I need to record that. That's cool. Yeah, so this is the adjustment, and then it moves. It returns to the center position when it didn't find it like around a perimeter of 0.2 millimeters in all directions. So if it found it successfully, it will keep the offset. Hey DFGA. So this is actually working, and before I had this working like that, thought for what? What do you mean, Sonic? Anyways, that's cool. This is the programming jig, and the result is looking like. Yeah, unfortunately, I would like. I don't know. Pogo Cincy. Yeah, that's the issue is the programming takes long, and somehow the control over MQTT with this Python integration it's super slow. I don't know, like each command takes like 1 second. Each movement it takes like 1 second to react, which is not fortunate. But as long it does the job, looks fast enough, yeah. I just turn it on. I mean, this is now doing only one row at a time. If I could turn it on and it programs like 256 MCUs at a time, because I need to change the pins, either that or I use like one pin only to program it, because the 2 rows are mirrored and I have like the pin order. This is so stupid. I could have placed the order correctly in both, like the same way in both rows. I didn't think of that it might be an issue. It's not like really an issue because I can attach the ground. I can attach the ground to like the interface, and it's still working. And I only need to program it once. Like as soon as we got the firmware working, this will be all right. Oh yeah, and it also, wait, before we turn this on, it will return to the initial starting position with offset, unfortunately. So if there is like a lot of offset, yeah, it's doing it 4 times. Usually if it succeeds first time, I will show you the result that I had when the print bed. Oh, by the way, you can see that maybe I had to be able to reach it, because I have like an offset of the programming pins. I needed to put the magnetic print plate a little bit in Y direction, so it will be able to reach all the corners. But the build volume is large enough for this thing. So imagine this was now a 16, but we did 5 tries each, so it's a lot of tries. 80. No. Yes. 80 MCUs. The programming would take a little bit longer though. So now it returned. And this is before I had the adjustment. And I had a slight tilt of the build plate, the magnetic build plate. So each row that I proceeded was slightly shifted to one direction. And the cool part is I can power all from this little power supply. This is the best. This and the soldering stations were the best things that we bought this year. I totally have to. Why is it focus? Focus. Okay, let me turn it on. It's set to 3 volts, and this is the result. As you can see, it began. Okay, now we have some code running. It had like an issue here. Is one LED missing? That was alright, and as soon as it like proceeded in this direction, it stopped, it had a shift and skipped a few MCUs, and then I corrected it and it was alright for some of that. That's why I added the shift, and so the next time we will program it. These are like in ready state to receive commands, and these ones receive the command but doesn't obviously it doesn't work properly because I would need it would need like to, I don't know, maybe I sent blue. Yeah, my code is not great yet. So currently some reds. Yeah, these are ready. These already received, and these have different code than these ones here. I'm just testing, and I'm the row controllers. I'm currently just programming with these pogo pins because there's not many. I can do that, and yeah, that's it. Oh yeah, that's interesting. When I connected it to the power initially, it was 1 amp or something. So they were more or less in idle state or running like in low frequency mode or whatever. And since every MCU that I programmed increased the current draw because the firmware sets the MCU to 100 megahertz. So that draws the most power, and the result is now a total of 4 amps, which is all right, isn't it? 4 amps per blade. So we that's okay. We are not running the LEDs at full power. It's only like a partial here, and we are missing a few MCUs here, like this row almost completely. So I guess it will be 5 amps in the end, and that's what more or less I calculated. It's now 12 watts, and it gets hot. So if you're wondering, we can watch it on camera. We can watch it on the thermal camera how it heats up. I have to turn it off after. I mean, it's not like hot. It's just getting warm for now. Oh yeah, let me disconnect this and connect here. Where's the thermal camera here? Here. Doesn't work. Why doesn't it work? Let me try to configure the video. Nope. It won't work. Okay, let me move it to another USB. Maybe that will work better. We were using, I believe we were using some sort of, where's the pink cable? Can use that. No pink cable. Eh? Here. Okay. Let me try that. Oh no, pink cable isn't like female. Huh. No, I didn't consider that. That's just too much work. That's all right if I can like align it properly at some point and then like I could add a camera to try to like position it or whatever. If I still had like the light placer, I would use that for this. Would be way easier, but I sold it. Okay, thermal camera not working. I don't know. It's not working. All right. Yeah. No. The hunting happens like every single pad. I have like the adjustment in all 4 directions, and that will incrementally adjust as we go. If it takes longer, it takes longer. I just don't care. I will have the first batch of boards is produced right now. It's 15 boards plus this one plus 3 boards which I still need to botch because Mizomozi connection is still flipped. But I will probably build the first setup only with 16 boards, and that will be programmed like within like I don't know 2 hours or something, which is all right because I can grab a coffee and I know. That's all right. Okay, thermal camera not working today, so I guess I could get a thermometer. Let me get a thermometer. I'll be back in a second. I know where that is. All right, here we are. Yeah, that's 40 degrees C right now. yeah, 40.9. Yeah, so still okay. Slight fever. Aldo? Yeah. This is alright, I guess. The issue is when I turn it over to program it like that, or I debug it with, no, debugging is on the other side with the oscilloscope. Because that way I only find out that it's, I had an issue. I'm really surprised that Gemini is so well educated on this WCH RISC-V MCUs, because let me turn it off. It was able to give me the hint how to turn on and oh no, Phew, this is not what I want. It was able to give me the hint how to finish SPI host. So basically, I had the issue. I'm sending like a packet of. Oh yeah, you can't read that. Let me get rid of that because that's quite the interface, quite huge. So I'm sending a packet of 16 bytes. This is the length of the payload, which is basically a forward signal. That's the forward command, and then we have the column, which is basically incremented here, and then the RGB. Oh, then the command, which is maybe I just commented. So forward target. You can cascade that. You have then forward target, and then it should remove like its own forward, and then this is RGB, and this is RGB8, and this is basically RG. Hoopala. Maybe I should move it slightly over there. Payload length. And this is RGB. Here we go. And this is basically just filler, which we don't need to send it right now, but I found out like we have the little MCUs have a FIFO of 8 bytes, and if we send like 8 more bytes, we will receive the data back. So actually we would be able to check, verify the data, but this is only between the level 1 and level 0. Level 0 are the small MCUs. This is level 2, which is communicating to the row controllers. How's the board? Oh, yeah, board's getting warmer. And it's still 40. That's alright. I have window open. Close that. Enough fresh air. Yeah, so I had like disabled that CS before it was sent, because my send command is waiting for the previous byte to be transmitted, so it doesn't stall the processing. But then I didn't have that. Why is the warning here? Oh, it's separate. Okay, here we go. Weird warning. Probably because you wouldn't be able to see it if it's far out. That's fair. Fair enough. This is basically waiting until that. Why is this in spaces mode? Which is wrong. Sending the data and then waiting would be done in the next command, but now I have finish SPI host, which does, it waits for the byte to be processed, and what also Gemini, hey TMK, Gemini suggested is waiting for the bits to be shifted out, which is flag busy, and this is basically while it's reset. That's weird. Anyways, while it's busy, it's just waiting. All right, so that's that. And yeah, that worked, and it waits until the SPI is done sending before it turns off the CS. What I'm also doing right now is I'm waiting just a delay, but I could as well, I don't know if I can I measure it? I could, what I could do, I could pull down Miso and then wait for the Miso to be pulled up, I believe, because once CS is registered by the other side, it will switch to push-pull mode, which will pull it either low or high actively, which will be stronger than the. Okay, so maybe that I will just note that idea here. Replace by Miso pull and test when other side active. Okay, so that's a thing that I can do. Then we have, yeah, that is done. That's just waiting, but now I'm missing something. Oh yeah, one thing that I wanted to do today is how you are experienced, and I want to take notes or hints from you. I could ask like Gemini, whatever, like always, as a suggestion, and I got also suggestion. So when I turn it on, I start a command and then I turn off the chip select. This is not necessarily, I can do this, or I can leave it the CS active if I only want to communicate multiple commands with one end. The issue is I don't know when a block starts right now. I can detect, all right, on the other side, I can do, this is what Gemini would suggest. There is no, I think the little ones, the 570, have like a command byte implementation, but there is not much information about that. If the command byte is not treated differently, it just ends up, you get an interrupt for that, and that's all. it's not treated differently. It doesn't have like an extra register where the comment is stored. It just resides in the FIFO like the other data bytes. So that's one way of implementing that. I'm not sure if that comment mode is implemented also in, don't see, oh no, I have to check if it's somewhere here. Okay, let me check that. Why is my documentation closed? Oh. Let me start Foxit Reader. Oh, I should not start it while the stream is showing it, because you can watch not my face, you watch this here. How hot is it? 43. 44. So if you're looking at those two, these are the programming pins. These two are shared, like the CS lines. The two red ones here are the two programming pins. And I didn't turn off. I have the code. It's commented out. Because I want still to be able, without power cycling, to program that thing. That's why I left these pins in the CS pins here in programmer mode, JTAG. But I will, in the end, I will just give it, I think, a boot time of 10 seconds maybe, to have enough time to be able to like power cycle it or whatever. In the case I really need it, I really need to reprogram it over JTAG, which is really an exception. Or I will only accept over SPI a boot sequence, like a command boot now or whatever, and then it's the debugging interface is turned off. So that's why you see like these pairs of red ones here. They didn't receive any RGB comment yet. All right. Yeah, Foxit Reader. No, I should. Ah, here it is. Oh yeah. There is no, it's not in my, yeah, multiple, they are not programmed. So there is where, Wagonload, you missed that part. So my programming jig just skipped those pixels. I didn't bother, I implemented a fix for that. It will just search and shift slightly, but not used it yet before the firmware is ready. All right, let me do that here. Yeah, here, this one, yeah. That was skipped. I didn't bother like to, there was no, the programming jig behind me, it just skipped this MCU with an error. I need to like run it again. But first we will figure out the protocol to communicate correctly with SPI. So yeah, it's idle. It's idling. My mouth is getting dry. I need more water. Get some water. Pining for the fjords? What? This, I don't understand this. More IPA. Like Battleship, yeah, almost. 45.9, so I guess we will reach an equilibrium at some point. I don't know all the Monty Pythons. I'm most familiar with the Holy Grail thing. All right, so how do we detect? Oh no, I wanted to check that. Let me. Nah, they're all right. I think they can run. We will find out in a second. Let me check what the maximum operating temperature is of these devices here. Here, datasheet. Then we have CH303, reference manual and datasheet. Okay, I got all the datasheet I need. Let's get rid of that. That's datasheet. Ah, that was operating 85. 8, it's 17. Operating 85 degrees. They have temperature sensing. Okay, and this one is, yeah, probably maximum 85 as well. So that one is also 85. So we are still fine here. We have more like 40 degrees still extra. We are baking them. Oh, the LEDs might not have 85 degrees operate. They probably have. Anyways, let's check SPI command mode if there is actually, but I didn't get anything from Gemini. Let's see, that was Gemini fast. Not sure if I still have the window open. I might. Let me check that. Oh yeah, here is my prompt was how to disable. Oh no, that's the other one. Oh no, I had more prompts here. Yeah, here it is. How do I detect start end of transmission at the slave end using CS? Slave end, I'm sorry, client end. Temperature. So start falling edge. So usually you have one as CS is inactive, and they just suggest, or it suggests, yeah, basically interrupt. So it just wants to, we could start basically capturing something on the edge and then basically clearing also all the old inputs and then reading it. And this is, what is this? Read input data bit. CS is low, start of transmission, prepare SPI, end of transmission. Yeah, that's the RQ handler. This would be the way of Gemini suggesting it. Now I still listen. If you have input for me, if you're familiar with the features, okay, we have duplex, supports data hike, blah, data ordering supports, okay, supports hardware, software, blah, hardware CRC, DMA transfer, supports modifying clock phase polarity, blah, blah, blah. Doesn't, so, okay, that's SPI features, I2S features. Nothing there, alright. DMA. It doesn't have, I believe this one even doesn't have a FIFO. Not sure, you would use DMA instead. Let me check that. SPI, I don't see, actually I don't see shift reduce text buffer address data bus. Yeah, that's what I thought. And if you compare it, like, it's so interesting because this one, it's a much simpler MCU, but it's differently implemented. It's a different architecture. It supports wagon loads. I do something to the clock to trigger this. No, how would I do that? DFGA. I can't, I'm not controlling the clock. I'm only controlling the chip select. So what we can do right now is using an interrupt for using chip select, basically the start of a transmission. That would be the simplest. Or we do like some sort of ID at the start of the transmission. But I would like to have basically on all CS, if there is some error going on and we are in the middle of I don't know what the state is. If we are in the middle, since it's a serial and we only transferred 4 bits and then CS goes high again, what happens there? Is it the reset? Does it receive a new byte, or does it wait for the remaining bits to arrive and then completes the byte? That would be wrong, and I don't want that. So maybe we really need to have some sort of interrupt control here. Interrupt types, SPI trigger mode selection register. Okay, let's see what kind of interrupts there are with these ones, because it seems like I'm not really good at receiving the comments, processing them correctly, and forwarding them right now. At least everything looks blue. That byte and oh, there is a buffer. No, buffer is just 1 byte, or is it? Yeah. No, R8. Transmit and receive buffer. Okay. Working, say, after chip select and say being low. Okay, that's a flag. There is a, oh, we are in 572. Okay. Toggle it twice, each followed by a specific byte. No, I mean, if I toggle it and if I'm looking at CS, then it's always clear that a message starts, a new message starts. There wouldn't be like I wouldn't cut up a message or something. I will just always transfer a complete message. I guess if we only sending like 8 bytes each, I could still keep like chip select. We can, if we are communicating with the small one. Traffic manager. Mechanical layer. Like we have a physical layer, if you mean that, or what do you mean? It's still 45 degrees. I don't believe it will get any hotter. SPI free, not free. What does it mean? FIFO overflow when receiving, FIFO empty when transmitting. Not with this attitude. DMA end flag. Okay. More half FIFO, blah blah blah. Okay, so that's interrupt flags. Let's check. First byte received in slave mode. Okay, but when does that happen? So we can do a specific implementation for that here on the small one. But I don't think that the small MCUs are the issue. We want like the communication on the other thing. DMA, FIFO overflow. Okay, what is this? Half byte and single byte. Yeah, you don't really want interrupts on that if you're running in megahertz realm. The overhead for each byte calling interrupt will be crazy. Bucket brigade, yes, basically like that. And there is always like a junction that currently is between 16 and 32 like new roads or new queues. So basically if we forward, we have like a new address which is an index of the next one that receives the whole packet. So that's like that, but the SPI is slightly different on the bigger MCUs and the small MCUs. The small MCUs are luckily at the end, so they're only clients. They mostly receive right now. The sending part, like if we fetch data, we will do that later. Most important is now we want receive packets and be able to program them in the end. That's the goal for today, at least. Would be that would be my favorite thing, getting the SPI working, so we can program that with the new firmware that receives LED values on each of the pixels. We program all the MCUs correctly, and then we use another MCU with SPI and USB to transmit a live image on that board. That would be amazing if we can achieve that. Stretch goal is uploading firmware over SPI. If we can do that reliably, we have one method which does not allow to overwrite itself, because how that thing works, like the small MCUs, they can load in SRAM. The issue is that not all the flash code is public. It's like in a library. We disassembled it on a stream before. with minor success. I found like I think one disassembler that did it more or less correctly, and Basil sent me also C, not only the disassembly but basically the C plus no the C code for that, which is approximated. Let's say, wait, let me, no, that's the wrong one. Where is it? Level 0 bootloader here. So this is all the I tried to run. This is not that. Wait, begin, end, flash ROM. There is only one function, not right. There is one function which unfortunately, like the library also uses code that's loaded in SRAM except for one main function here, this one here. This one isn't stored in SRAM, and the issue is if you run that, it's loaded from flash while it's running. A, it's slow, and B, I can't overwrite this section with new firmware. I have always to have the bootloader in a different part of the flash, which adds new issues. I can never update the bootloader and so on and so on. So I want this part basically to be in how's it called, HiMem. I think it was high or some, no, high. Let me check again. I've used it, high code, yeah, high code. HiMem. Here. So this is the only thing they messed up doing the library, that this is not in high code. And it's a weird function. HiMemSys, yeah, MS-DOS, which HiMemSys was doing EMS, XMS loading, like you had an overlap of, what was it, 52 kilobytes of the highest possible segment with EMS, and you could load stuff in that, like system stuff or drivers. You could load in that area. What? Yeah, they say it's 64 kilobytes, but it was overlapping. I think the page size was 16. No, wait. Or was it 16 bytes? Oh, it was 16 bytes. So yeah, 64 kilobytes minus 16 was the area that you can address above 1 megabytes of RAM in 16-bit MS-DOS. Yeah. All right. Yeah. So it's a weird thing because it does something like you have. Oh yeah. This is. Oh, weird. Okay, I have the specific address in my code somewhere. Because I tried. Oh yeah, here. SPI digibit circuit where I needed to control it from a different PCB to reduce the wires. I connected CS pins to a, okay. Yeah, so this is the same disassembly, and but weirdly I added these functions. I tried to use the ones from the library, but it would just lock up. So either the calling convention is different from within the library, or something is weird. So I need like the disassembly of everything, including these two, because these would be enough for me. This one like EEPROM command does nothing except for this weird boot up of, where is it? Yeah, it does this weird reset or whatever of the EEPROM, or I don't know, driver, and then does barely anything, just calling the other functions. And then it has, I think at the end, yeah, it has like a sequence unlocking diagram. I could ask them. I don't want to. Maybe I could convince Patrick. He did like he published like all the code for the other MCUs, this 003 whatever. When Thea pushed them to release them, they put it on GitHub. I mean, we can try just the disassembly, and if that doesn't work, I can ask him. But he's hard to reach. He's so busy. Just, just like I am, most probably for the most people. Yeah, that's probably the issue, or the calling convention from within the assembly is different. Like they use a jump. If you look at the um, if I don't know if it's RISC-V or whatever, but they call it using a jump and writing like the return address. You have like a register, I believe, and there is no like call or whatever, and it might be that the stack frame is different in C. Yeah, first of all, this is for the SPI bootloader. So we have, show you we are now all over the place. My goal would be like doing first, I want the forwarding of a comment and have that comment to be like intact, because now I have the issue. If I want to upload a firmware, it's not like one connection, it's just going like step by step from one controller to another until it reaches its destination. Hesman days. What is Hesman? Okay, let me show you. Now I messed around in that code. What did I do? Oh yeah, I deleted that by accident. Okay, nice. How do I get my window back here? Yeah, okay, here we go. So I will show you the beginning of the bootloader, like how I wanted it to look like. Where is it? Startup source here. Okay, so the bootloader would just initialize everything as okay. So it sets the LED to red. This is what you see. Oh, bye the Shipu. What you see is when the LED gets in ready mode, then in it initialize client. I wanted to change the color after that, so it might be green. It's too bright right now. I want it probably less bright than that, because I find it's quite bright. This ready state shouldn't be that bright, because that's might be too much current at the time. Then we have it. changes, it flips basically to the FIFO to receive. And then what we do is we assume first byte is the length. Then we have basically this is how it would work. We receive the length byte of the data that's following, and then we have we receive that, so we wait until we received all that data here, and then we analyze it. The first byte is basically the comment. There is no forward here. I will also these are the system comments. I will change them. So what I wanted to reflect in these comments would be like write memory byte, and then write address block, and write is basically flash, and then there is also erase, which is in the wrong here. Erase block. So in the end I will rework that. That didn't calling those doesn't work. So this is just more or less a scaffold. So I will be able to write somewhere into RAM. In that case, I have like a data block of whatever 512 bytes. I think 4 kilobytes are the flash. Was it? I think the length, if you look at the code, it might be 4 kilobyte pages that you erase at the same time. So you would need like 4 kilobytes of memory that you can just load over SPI, and then erase the area and flash it or whatever. So that page by page. That's a tree. It's quite simple. I will paint it for you. That's quite simple. Okay, here. This is your diagram. We have plenty of that's 570s. Then we have this is level 0. Level 0. This is level 1. This is SPI. Then we have exactly like that. Then we have oh, by the way, there is more. So we have this is all level 1. SPI. Each of those MCUs has an individual CS line, so I make it quite thin. Here. 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 And same as with Uppsala. This is level 2. These are both 303s. It's a V303. This is also V303. We have this part, the count here is 16. This count here is 32. 32, and this is 1. This is basically the physical board, as you can see here. These like there are like 2 rows are the 32 MCUs. This is level. Yes, there will be L3. L3 is now on a board that's not there yet, but here is basically we have the interface here, edge connector, and now we have maybe the interface board, and we can temporarily we can connect it to a microcontroller with SPI and USB. This is our goal for now. That's USB, and we can control basically send SP. This will be then L3, but L3 L2 are identical, because I guess I will use a microcontroller that's similar to 303. I think so, except for the last one, which is a little bit different because the SPI works different way. But I want to use like the command, the structure. A packet will be basically first byte is length of the packet. Then you have the command, basically, which is, I don't know, command byte, and then you have data. And then padding is done, if you have like a fixed packet size, is done with zeros, which will be interpreted as length of 0. So that's quite simple. In that case, it will not expect any more data, so it will always restart, because it's 0, 0, 0 until we get the length of something else. If that works correctly and there is no like error or shift or whatever. One thing that we can always add is like a CRC to check if we're in line with everything. Especially for writing firmware. Oh, chip ID, that's interesting. I read out chip IDs of these MCUs. They don't have a specific chip ID. The chip ID is not written, or I don't know. I got like a batch of clean chips that have like 0, or they're started at as. I read only the first one, and it started at, but I don't believe it. It's a coincidence. I read 0, like it's not 0. It was like in the center was like 1 digit that was different. They usually have a chip ID, but they're addressable with the CS line, so they don't need. Oh yeah. What do you mean SPI? There is no address, there are only CS lines. So basically they have the address is the CS line. Forwarding protocol. Yeah, so forward would be what I can do, I can compress data, because forwarding would increase the length of a packet. And I don't want to increase it probably by 2 bytes, and I don't have that many comments. If the highest significant bit is 1, then it means like the target is the lower 7 bits. I mean, so we could encode it. That's why I want to change the system comments to below 80 hex. So basically the forward is exactly the CS line that the next one. It's really the physical address. There is no like logical address or anything. Or I mean, it is logical, because you don't say it's PA0, PA1, whatever. It's just 0, 1, and the MCU, the firmware of level 1 has like the list of, let's see, level, let me show that, where is it? Where's my level 1 code? Huh? Here, level 1 code. Okay, so basically, it's send LED. Oh, you can't read. That's like it. This is when I forward an LED command. Yeah, basically it's a basic tree. If logically, everything is like we have 32. They're all addressed 0, 1, 2, 3. This is the host. These are the MCUs. This is this is basically level 0. Level 0. Then you have like the bigger MCUs. This is level 1. Level 1. And no matter what there is, you can always, it's like recursive protocol, so you have always like a tree. You can do that, you can do more and more and more. And this is level 1, this is level 2, and so on. So you have like the nesting in the protocol would be then you need to, at the beginning, you need to know, okay, I'm addressing not level 2. Let's say we are level 3 here. Yeah, but the IP address is getting longer and longer the deeper you want to go. If you want to address like a screen or a mouse or whatever peripheral, you have like an added address more and more. So let's say I have a payload. Let's say this is my payload. It has like 6 bytes and I'm at level 3. I want to send it to level 2. I just send the 6 and 6 as length and the payload, which is the command, and so on. If I want to send it to L1, I would send 7, then the 80 or whatever, 80 hex plus address basically, or index plus index of the line here. So this is index. And if I want to send it not to this one or this one or this one, there will be, and now I had to, so this is 80 plus E, then we have 80 plus, oh no, sorry, other order, 80 plus E, this is then 8, because we have 8 byte of payload, and we have 80 plus J, that's like a unique address for going I here, J here, and then we address basically every single, in this manner. We can just extend it. If this one probably won't implement the forward, that's why it will either ignore forward commands or most probably just ignore forward commands if it doesn't have any more clients in the tree. But this way it should easily work. Oh, the L2 knows, because the highest significant bit of the comment, this is, it will interpret this as a comment, and the comment for it is 80, which is forward. Oh, yeah. So this is what each MCU SPI its own RAM address. So you mean like each it is basically that. It is like not you have not like a 4 byte which then is like segmented in, oh, let's say the first kilobyte 4 kilobytes is because then you have like you need like a logical mapping, and this is more or less a flexible addressing style. And then yeah, so basically this interprets, oh yeah, um, level 2 basically sees, oh, I need to forward anything that's behind that. I need to forward to the next one, so it will remove that byte and do a 7 and the command, and then do that. It doesn't even need like to change anything in here. Payload is CRC'd. I believe the address not. It will. Okay, so L2 would then pick the fourth CS line. This is 4. Remove that byte and then forward anything like 7 and whatever 80 plus J. 80 plus J. And then the 6 bytes here. This packet will be then sent to line 4. Oh, let me shift that. So this is what happens on L2. It sees, okay, we have 80 plus, this is the command is 80 plus I, and I is 4. That's how we can do that, and basically remove that 1 byte from the payload. Yeah. I guess we can save 1 byte. This way we could use like 80 plus address and move on, but that would be a wasted. I don't think we need, like, we will have 256 comments. So if we use like 1 bit, the highest significant bit as an indicator for forward, that will be right. Hello, Paterelilis. I'm doing fine, and you? Right, so this is what I thought we will do right now. Okay, we need to modify that in that case, not this one. This is the where does like level 2 know from where its section of the address is? Like, or how does the lowest level know its address? It doesn't know how many layers above it there are. So it would need like some initialization and so on. So you cut the address. I don't see like the difference in, yeah, I don't see the difference. I mean, I would never have like more than 120, more than, what is it, 127 chip selects. There is only one level below. Or do you want like to like recalculate everything? Yeah, I believe that's adding complexity to a simple problem right now. I don't want to overdo it, because then, um, I mean, I guess the top level always knows what kind of levels are below, but it doesn't need like to shift around to peg the address. But I know what you mean. It's one solution. I don't want like a lot of, I don't want any processing at level 2, because the issue is like we have two SPIs that are independent, and I need to forward. Okay, yeah, wagon loads. In that case, um, the issue is with your suggestion that, um, the lower level needs to do active fetching of the data, but the higher level L1 in that case, has to handle like a lot of requests at the same time. So and since this is the master, it needs to, or the host, it needs to either poll if they want like to fetch something from memory, or it needs to transfer the memory there and they're just taking it out of their memory. But basically, when we get some data in the mailbox, so where is the mailbox? The mailbox is maybe on the top somewhere here, and then it asks, yeah, give me data. So you get like, this one needs to poll, oh yeah, it wants data. Then it received the command, get me that data. So there is like a lot of communication going back and forth. What How I think is most performant would be if we have like a supercomputer, or whatever, the host is the PC, and it wants to send, let's say, just simple RGB or code or whatever. It knows where to send it, and in my case, like the thing that I would suggest, it sends like, um, but where are the RAM boxes? Where is the RAM? So when I send a packet, I want it to be transferred over DMA or whatever, buffered here, and instantly, like, we chop away like the first byte, maybe replace one byte, and pass it over to the next DMA. And this data that we just received, oh, it's wired like that. We have host, client, host, client. It's like that. Each MCU, and we have limited RAM here, we have limited RAM here. So we chop off like the first byte, or replace like the second byte with the new length, and send this as DMA, to to the next SPI, which and at the same time free up this SPI to receive like the next packet, which is probably meant for this line or whatever. And since I want to, maybe they would have different clocks. It might like get clocked if these are slower than this one here. But from what I saw, this SPI connection is the fastest because it's the shortest as well. So basically, we will be, this one, we just juggle the data and pass it over to the next one. And I don't want like any processing of the packet here. It will just chop off the forward address and forward it. That's what I think. Now let's implement this. We can always improve it later if it doesn't work. Okay, this is what usually you can signal to the master using the CS line because this is an individual connection. Let me think. The issue with that is that you have like active low, like push-pull mode. Usually I leave them in high impedance, so they're like unknown state or pull-up. I think I even put it like a pull-up, and as soon on the host side, and as soon as they are like triggered. No, that's not. I think it's push-pull. Let me check. Not that I tell you BS here. Level 1. Okay, these are the CS lines. Yeah, no, they're a push-pull. There is no way we can do that. We would need like to use pull-up, pull-down. But in that case, CS would get way slower because the slope is quite. So either we use like push-pull to have like super fast switching and then polling, or we use some sort of like pull up, pull down here, and the client would be able to actively push it low to enable like signal, here I have something for you. We have to test that if that works, because especially when we are running calculations, I don't want to poll 32 MCUs to see. Yeah, that's one thing would be like fetch mode, where the master is signaling. This is what I intended, but it's quite dangerous because you can cause shorts if there is like miscommunication on the bus. So CS is like chip select. So it enables the chip to do whatever, communicate on. And issue is, whenever this chip select is active, the SPI will take the meso line and push-pull it. So if you have like two clients on the SPI that are currently in CS low, they will both like counteract on like cause shorts on the meso line, which is not great. We don't want that. So what we can do is, let's say these are the chip select, and then we have the this is what I don't know if you missed that part when we designed everything. CS is currently only driven by master. That's currently, but it's not necessary. We can do that, but in that case, if the client is driving the CS, it has to disable the meso capture until, like, if you use it as a signal, then it would need like to trigger it while disabling the SPI, so it doesn't take over a meso, and then it needs to wait for the master or for the interrupt trigger master fetch. Yeah, so basically CS, if we have like an interrupt, I don't know how many interrupts you can have there on all, because 32 lines are a lot. But if the master catches, oh, there is something going on, like if it constantly checks the register and sees, oh, this CS doesn't match with my current state, means that client wants to send something. But if the client only just pulls it down for a short moment to indicate, here I'm ready, I have data, it will just like send like a signal shortly, and then the master pulls it down to fetch the data. That could be one way of, but this is like a huge topic. We don't want to. Yeah, so let's say the host transmitted all data that it needs, that the clients needs for their communication, for their calculations or whatever they do, and now it broadcasts, or it sends to each individual MCU, I'm turning off SPI to fetch the data. Okay, so it would basically disable the chip select for, I don't know, until it receives the packet or times out or whatever. And in that case, all the clients are capable of sending data over the CS line using the clock of the SPI. So that's like a different mode. There is no address. The CS is basically the address. There is not like, it's not like I2C, where you have an address that you're reading and writing to. It's just an endpoint that receives data, and we have like the logical address is our. Yeah. It's just physical, and it transfers the bits to that, and this one receives the bits. If you have like, you can implement this layer on top of the SPI. If you say, okay, the first byte is the address of the memory, and then the second byte is what we write to the memory or whatever. So we could implement that on top of this layer if we address each individual. So in that case, when we have in fetch mode, the master or host would basically switch all the MCUs to RS232 line. I have no clue what. I guess. So let me finish that. So basically, in that fetch mode, however this is implemented, it would set the clients, okay, you can don't use meso, use your CS line to communicate your results. And then the host will clock in all the bits at the same time. So we get a stream of 0 1 0 1s I have no clue what RS232 is. Anyways, we get all that bits simultaneously. That's why I designed the system to have serial port. Yeah, but serial port has like the parity and so on. We don't have that. A serial port doesn't have the clock. It can have the clock, I believe, but you have done like the synchronization is done with the extra bits. All right, so that's why I put the CS lines here on the registers A and C. So we have A0 to 15 and C0 to 15 is to receive. We need only like two read two registers to receive all the data. So this like bit banging all the data and store it away. So we can receive it really fast and then we need to forward it really slow. Ericon simultaneous, yeah. It is designed for this, like fetching it in parallel, and then we can use at the highest level. They most probably will be basically that's the same. Reverse broadcast. Yeah, basically it's a reverse broadcast, and we can decode, like descramble this all entangled data, which is like the serial bits in a parallel stored in a parallel manner. We can decode that on the FPGA and then send it, or on the PC that's receiving the data. So we don't need any processing. The issue is that we receive a lot of data here. I mean, these are processing because these are doing the calculations. So these are probably busy with communication all the time. Once they receive that, they will either try to send it over SPI up the stream, or they use the same method, and then it will just get congested and congested. And we have L0, L1, L2, and L2 has 16 parallel lines. Whatever we do with that on the port here, here on this port has 16 parallel lines because it's only one chip here. Yeah, I can buffer. We have 200 kilobytes of RAM here. No, 200? No, 60 kilobytes. We have 200 kilobytes of flash. Let me check that. But we have plenty of... wait. Datasheet... 64. 64 kilobytes should be enough for everyone. We only need we can store the whole contents of a Commodore 64 when it's fully loaded. Including video RAM and keyboard buffer. But not SID. Oh wait, no. No, video RAM is mapped. Yeah, the VIC state. No, what's the... That's the name of the video chip, isn't it? I mean, because it's just another... Okay, maybe not all the states of the peripherals, but anyways. At least the RAM. VIC and SID, yeah. Yeah, SID, but I think it's also mapped to the RAM, isn't it? Yeah, I believe it's mapped. I would like reverse broadcast on all the lines, but L2 will have 16. Yeah, it has to be mapped in that range, but I don't believe we need that much. If you whatever, I'm talking too much. It's now we are 1.5 hours in, and we are just explaining. I hope we are on the same page now. Let's implement it so we see some action here, and my board doesn't get any warmer. Okay, we reached the top with 45 degrees. I was anxious it would get hotter than that, but it seems to be all right, like 20 degrees, 23 degrees above room temperature. Yes, it is. Ah, yeah, it's warming. We can do as it's a if the SPI doesn't work, we can use it as a fondue cooker. We can melt. We can melt my. I need some energy. Let's supply me with some energy. I didn't eat chocolate for 2 weeks. No, I had some chocolate today, like another Easter egg. This is still from Easter. I didn't eat a lot of sweets lately. Has anybody tried out Andreas Spies AI ESP toolkit? No. I thought you stopped making videos. Didn't he quit? I didn't pay anything for that. Yeah, 3 kilowatts. So I'm retired as well, because I'm posting who knows when. I don't know how he could manage that tight schedule, like every week a video. Yeah, wagon loads. Then it will be an address of 2 bytes length, because I just keep it simple like that right now. So there doesn't need to be any logic on the lower levels. Okay. That's a lot. It's 150 grams. And I had like 60 of it or 70. You have to have a schedule. Yeah, that feels like work. I don't want to squeeze out projects. I want to something that I am satisfied with and that feels complete. I know it's bad for my finances, but something Zach Freeman. What? Okay. Someone. Hey, ITG. Yeah, I don't know. I don't work like that. But this won't be done when I publish it because I have some issues. I need like to. Uh, the the budget isn't sufficient for completing it right now. Well, I guess it will be. What is it? 8,000 MCUs will be still good enough for now, and the 64 64,000. Okay, someone's writing me. Let me check what I get here. Who's writing? Who's writing to me? Oh, Johnny. Yeah. All right. Um, that's the microscope. Right. Let's continue with that. So the issue was, yeah, this is like a rough thing, and I didn't have anything that that does the receiving part. Okay, let me just see if it's still working, like this part. Okay. Let me program one row with that thing. Let's program this row. Yeah. There was a warning or what? Yeah. What was problems? Okay, yeah. While loop has empty body. Which one? Yeah, I know. Oh yeah, that's a copy of the code. New line. Let me compile that again. Why doesn't it send it? We were successful uploading it. Were we? We turn it on. I go. But that's only warnings. It compiled. Is it why didn't it upload R plus plus while set LED, send LED? It has this delay US. We can copy that from level 2. I have to copy to have like a same code base everywhere. Init, send, receive. Okay, we can just remove these warnings by doing that. Okay, let me try to program it again. Alright. Yeah, these are not receiving it correctly. They just receive, so my test doesn't work here. Something's off. CS. Okay, let me get this one. I hope I didn't screw it up here. And these are the debugging pins. Because that needs to be the same thing. I hope this is correct. Oh no. It fell off. Stupid thing. One cable fell off. Let me... Okay, how do we do it? Let me turn that off for a second. Okay. And I will reattach this wire that detached from my test device, because I need to test now level . This is still off, okay. Surgery. Programming pin here. That's good. Okay, let me upload that firmware. Oh, interesting. Oh yeah, it's blue. So this is the, I don't know if you can see. This is the only one with the right firmware. It's only sending blue for whatever reason. That's why probably it didn't work before. So like the first MCU in that row has the same firmware as all the others. It's also only blue here. Let me switch to that. So there is an issue with the code. Enable, that's IRGB. I don't know, I don't have this saved because that worked before I made this here. No, it's not continuity because it doesn't work. No, it's only this one here. This one is still only blue. So what I did last time, I took this code and put it in the method, but I don't know why would it do anything to that. Let me reset. Oh, now it's working. Huh? Weird. Oh, wait a second. I know why. You know what the issue is? I'm sending the shifted bytes already here and I shift them again. that will never work. Oh, so stupid. Oh, damn it. Yeah, that's why it's always blue. So it actually, the forward code worked before. I had just a stupid error. Yeah, this works now. But I see a little silhouette. Scaramouche, little fandango. Yeah, RGB. And this needs to be G. Okay, now the code is correct. Let's upload this to that again. This was ground. Yeah. And I need my probe, my pins again. Yeah, but thankfully I have this test code here. The only thing that I can't test is the forward because I have only one level of SPI here. Where are the pogo pins? Hey? I lost my pogo pins. My programming pogos. Programming pogos, where are you? Okay. Where are my pogo pins? If you see them, tell me. I can't see them anymore. Did I drop them on the floor? Hey? No. I had like second set that I used to program this one. Oh! I heard something falling. Ah! Oh, they were on the floor. Yes, I found them. Here we are. Okay, that's my programming setup. Let's do output. Here we go. Initialize. Bonk. Okay, so here again, the programming of this code will happen. I hope they're the right way around. Nope. Wrong way around. Or I'm wrong. Try again. Yes, that was right. So now we should see. Okay, this is now doing something. Yeah, so this is now only doing like the demo mode, but we can now activate the forward command from the host, which was the other code here. Blah 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 code. Blah blah blah, Mr. Freeman here, and then said okay, forward code. Let's try it. I guess so this way around. Okay, first. I don't need to recompile it actually. Uh-oh. Okay. 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 Okay, Now let's review if forwarding works. Nope. Okay, let's reset it. It might have just received anything. Nope. This one is still... That's weird. Why is this one? Huh? Oh. No. Wait. What am I doing here? I am sending set LED data. Oh yeah. Wait, set LED shift left. That, yeah, and send LED, that's alright. That's correct. Huh? Weird. This one is still counting up, but it's the other ones are receiving blue. Why? Let me download every single one of those. And it's why is it twisted like that? Still too twisted. I will break it at some point. It's just a demo board. At this point. Okay, this way around. Nope. Come on. Doesn't want to. Now it did. Okay. Still all blue. Now let's power cycle and see. Yeah, but also these here receive only blue. So let's take a look at the code. Maybe I did something except for this one. That's weird. Yeah, let's take a look at the code, or we can debug it. I want to see what we are actually sending to with the oscilloscope. We can check on the level 1 data or level 2 data. That's easy to debug because I can just check the pins are exposed. Okay, I can just stop and then see what it's sending. We don't have CS, but let's see. That looks like blue, 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 blue. That's just the 8 bits that are high of the blue component, the blue part. And there is, I believe there are like, this byte is green, this is red, this must be, no, 10 is, one of these bytes might be 10, I don't know. So what are we sending here? So this looks like the whole packet. Let's analyze the data. We don't have a clock, so we can't decode it correctly. I was just too lazy. Or I would need like a third hand to decode this with clock. Let me run it with, I believe this would be, yeah, this is the clock. And this would be the data. I just need the probe really to be steady here. And I also need this ground. Oh, it's so difficult. Do I have more grounds here? Let me check that. Let's reset, that's ground. Yeah, I don't want to reset it. I did this, ITT. These are all programmed, like this board is programmed by the printer. I did it only, I have like a code that works row by row, and now I have like a few that don't work. Okay. Let me just pause that. Okay, we are receiving always the same data. Yeah. Oh, interesting. It's always sending the same packet. I will use the programming thing. I showed it at the beginning of the stream. You can rewind and watch it. Okay, so we have the forward signal, then we have 12, which is the address, then we have 10, and then we have, it's always sending the same thing. This has still the forward address like an extra byte. Okay, now I need to find out why level 2 is sending always the same packet, and why are all of those receiving this packet. That shouldn't happen. It's weird. It's probably a simple mistake that I did. Okay, let's take a look. Oh, this is annoying. All right. Okay. Hey, Chris. It's getting hot. I need to be careful with that. Don't want to short anything. 45 still. Yeah, now I programmed only the row controllers manually because I'm changing those on the fly, but okay, I'm wondering, we are send SPI host. Does it reboot? Maybe it's in a boot loop. Or do we need like, okay, let's try to send something different because now we have R is like really high. I want every packet to be a different R. Okay, let's do that. Or we can send a rainbow by giving it a specific, displaying the address as rows and columns. So would do this will be a row. Row, we can do shift 4 because it's only 4 rows, 16 rows, and then we do blue is basically call shifted 3 bits. Okay, so let's do that. I don't need that part anymore. Oh wait. Yeah, or whatever. Okay, let's program that and see what happens. Nope, wrong way. There are two possibilities too. No, you have you have to switch it twice. Doesn't want to. Ark. Come on. You detach the probes. Okay. Yeah, there was a lot of ground. All right. So this is interesting because it works, but the addressing here is, you can see from, if we look at that, this is 0 and this is 1 and this is basically red gets, so it actually works. You can see it on that, but why is this one this one is still not programmed? I need to reprogram this one here with the right code. There's L1 code. But the forward, this is just a hack. That's not like actual forward. Come on. Okay. Now it should have the right code. Yeah, alright. Oh, this is not, you can see that on the camera, right? We should now cycle green so we can see that actually something is happening here. So let's do that. And then we will run the programming of the MCUs again because we have some skipped MCUs here with the whole row. So you will be seeing that, and we can code while we reprogram it. I like it, Picasso. Okay, how fast is it though? Wrong, wrong, wrong. Yeah, they are not programmed. Crisis, yeah. Probably. It should have enough computing power. Let's calculate the power that so we have. No, it won't be able because we have 100 megahertz, but it's only integer. So 100 megahertz times 512 is 51 gigahertz CPU. It can run Crysis. Every LED will calculate its own pixel though. Brain of the size of a planet, really? Is it a wild guess or do you know it? Okay, let's let them. Okay. Okay, I don't need to receive anything here. This is level 2. Why do we need to wait though? We don't need to wait here. Okay, we will remove this later. One change at the time. This is just an increment, and we can just show R here, and we can. Oh, what? We can do like that. Huh? What? Why is it? Let's do plus R shift 4. And let's do minus 3. Okay, this is some sort of color cycling, and yeah, let's try it out. And then we will remove the delays. one by one to see. Okay, this is quite slow right now because we are delaying everything. The state of the first LED is reflected in the LED of the row controllers. Yeah, that's quite boring, isn't it? Let's delete the delay ms here and the delay microseconds here, and that should be a little bit faster. We have another delay. We might want to do that at some point, like shorter, make it shorter and also increase the speed and see what's happening. Okay, let's try with the delays, which were like a lot. That should double the speed. All right. Oh, I'm recording this. Okay. Yeah. That didn't do much. It's double as fast, but not as great as I thought it would be. Yeah, not really, because that's a hack, bloody hack, but more or less. It's not like an actual forward. I will show you, because currently I'm just expecting a packet, and then not even analyzing like the forward. Yeah, I'm taking. Let's see here. This is basically. I read data until I see either it's mode 1, which means it found the start of an address and the start is D6, and then it reads just 16 bytes and then just sends repacks everything, which is not. This was just a bloody hack to see if it's working, and we need to rewrite this to work properly. But I want to make the transmission faster. Let's go faster here. So we have delay microseconds. What about delay microseconds? Let's say we can check how fast the clock here. So these are 10 microseconds here. How fast is our CS here? Oh, it won't be as fast on all the things, but I guess we can do like 1 microsecond. That will also work. Let's try 1 microsecond. What is one? This is 5 microseconds. Oh yeah, 5 microseconds is that. Okay, let's do like try. Yeah, but where is this other delay coming from? Oh yeah, that's the old one. So we have 20. No, that's correct. 20 microseconds. Let's do 3 microseconds and see what happens. If all the channels, because there is a weaker channel that only supports 2 megahertz. So 2 megahertz is half a microsecond. Should still be alright. Yeah, there are a few pins which are only 2 milliamps or something. And then we will increase the speed, the SPI speed, until it doesn't work anymore. Okay, that's it. No, there is no delay in these functions. The only delay is the slow clock speed, which is 1 megahertz. 512. Each of these updates here of this pixel is a whole update of the array. You can see that by when we see like here these passing. I think, yeah, it must be. Okay, let's see on the scope. It must be really fast, but yeah, we get a full update here. Let's see on the clock here. Not on the clock. Yeah. Oh, this is the data. Let me check the clock. Yeah, it's quite tight. Okay, stop. Measurement. Oh, that's only 200 kilohertz. Okay, let's increase that a little bit. Oh, that looked better when it was defocused. Okay, let's defocus then. Okay, defocus. And improve the SPI speed by setting the prescaler to 8. I hope that works. We get issues with that. Okay, let's see. Okay, that's better. Now I want another function here. Okay, we want, but it looks quite stable for all the channels. Do you think we can go higher than this in speed? At some point it will start falling apart. If you have an integer plasma, please give it to me. Let's see how much. Yeah, let's find the limit. It's currently I guess the limit will be, this is 8, it's 7. Oh no, it's 7 megahertz? No, it is? No, let me check that. We can't go much faster than this. This will already have errors. Okay, let me. We don't need more than that. I will show you what it actually does, or calculate the actual frame count. Alright, so this is what we got. Yeah, we have, oh wow. Okay, yeah, this is the limit. Look at the clock, how it looks like. We can't go much higher than this. This is already 7.5 megahertz. Okay, I can try to go higher, but the clock looks like it's not sharp anymore. Yeah, that's like you have like some capacitance going on here already. I guess it might work, but it will probably have some issues. Okay, let me try. Like measuring it, attaching something else. Okay, this will cause errors. Now we go prescaler of 4. Alright. Yeah, this will be now 16. Oh, still works. Oh, 16. Oh, you can see here now you can see 16 megahertz. Okay, let's scope. Okay, this is going to be amazing. Okay, the issue is that I'm with the different ground. Let's measure the clock. Okay, this is what we get. The clock, 15.2 megahertz. And wait, if I measure it, it'll probably cause the data also. Yeah, I think I'm causing issues here as well on the array. That looks weird. I'm not sure. Maybe I am weird. Okay, let's try. We can go one more prescaler of 2, and then okay. I have recorded it. This is prescaler of 4 at 15 megahertz. And yeah, we wanted to see what the packet takes, like the time for one packet to update an LED somewhere in the array with a specific address. We can measure the time frame. Oh shit, too late. Or did I? Yeah. Okay, so that is one packet is round about 10 microseconds. So we can do 1 pixel is we can do only 100,000 pixels. 100,000 pixels per second divided by 512 is 200 FPS. Ooh. Okay. I guess we have to compress data then. But we are sending full 16 bytes and we only need 6. So we can do like 400 FPS with SPI without any like data fetching, only sending data in one direction. Alright. Yeah, let's try prescaler of 2. and see if we get any data through. Moment of truth. Okay, recording here. Prescaler of 2. With my math calculation. Oh, the calculation is quite easy. I will show it to you. I can't program it. Come on. Okay, now it took it. Moment of truth. Still works? What? No. This is at its limits. I can't go like 32 megahertz is like crazy. Wait. I need to zoom in. Oh. Now the MCU stalls. It runs it like each byte at that, but it needs like a breathing pause for fetching the next byte. So we are at its limits, I believe. Yeah, there is no like, look at that. If we send faster, and I don't know what is this. I have no clue what the frequency now is. If I do it like that, yeah, 30 megahertz. No, I don't use the DMA. Probably with DMA it might work faster a little bit, but yeah, Prescaler of 2 doesn't. Yeah, look at the signal. The clock is already very jittery, especially in that transition here. Our Schmidt trigger will go crazy. Okay, I believe Prescaler of 4 is Looney Express 3.0. Yeah, alright. We stay at Prescaler of 4, probably for debugging something else, because it's not much faster. We have some stalling without DMA. We'll revert the changes and then we are good. Here we go. Hello, I am 15 megahertz. What I could do is I could increase the clock frequency by like another 16% or something, because this is running at 120 megahertz. 144 was not stable without external crystal, but I have crystals, although these have the wrong capacitors attached, so I might need either to fix that or it won't run and then fall back to a small mode. Yeah, anyways, let's I need like an integer plasma, please, for an array of 32 by 16. Oh wait, I can ask Gemini. Made that plasma. Okay. I need also to do the addressing, because we have I think this is 0, and then we have we need to change that. SPI, okay. Oh, see. Oh, yeah, okay. Any matrix. Do I Google that? Oh, that's GitHub. Noise, Eno. Oh, okay. Animation collection. Yeah, I found it. Okay, let me take a look. Wait, it's one big file or what? Ah, okay. What do I take? No, it's not noise. Oscillators, pick, rendering, Eno, animation collection. Is there a plasma or chasing spirals? Can't wait. I find plasma there. Oh, it's doing it. Okay, we have know what? Okay. It's weird what Gemini does. What Gemini does. Let's go to we have an FPU on the main MCU. I hope it's fast enough. Where is it? Level 2 here. Let's add new file. Oh, plasma. Let's see. Okay. Let's add the code, which is, yeah, it does a sine table, which are right in it. Okay, let's do. Oh, we should maybe call it a H file. Pragma once, and then this is where we do the pre-calculation. Close that. So this is the sine table. Okay, we have pi. What is it? M pi. 1 pi. It's defined? Really? Oh, it is. No. Huh? No, what? This is 1 by divided by pi. Oh, this is the okay, yeah. Here, 256. That's all right. Then we have this pre-computed. Okay, then we have time and plasma t 0. Okay, and then we don't have that. We have. Oh, you know what? We don't need to maintain like a state here. Oh, plasma, and then just do an integer t, and we need an array which is unsigned t. Okay, so (32 by 16). All right. All right. This will work later. Don't animate it here. This is also spaces. Come on. Oh no. I don't need that. Clear screen. Oh! There is a clear screen character on the escape code. What? I didn't know this. Okay, remember, there is an ANSI escape code for clear screen. That is cool. That's a command line ANSI plasma, which is really cool. Okay, height is 1632. Height width. Ay. Let me do that. My code conventions here. Integer math value blah blah blah. Yeah, that's some code. Square root. Can we do f square root? No. Shoot. Okay, color index. Yeah, blue-red gradient here. Yes, I can. CDC if I attach it to another USB native USB MCU. We can do that. I would need like just to forward again. So this will be, but let's finish the plasma first. Then we can think of streaming. Color index. Oh, where was the color index calculation? I missed that. Color index value divided by 2. Really? We can also shift, but I guess we'll do it for you. Okay, here we go, color index, and then data. data y times, yeah, it will automatically do that, plus x. Okay, this is our color index. This is, we will see what kind of plasma we get out of this one here. Load range, blah blah blah. Don't need that. UN32, that's plasma C. Now we need to rename it to oh shoot, wrong file. ITT, when I used my jig there, there was no error correction when it didn't make contact correctly. So it skipped a few of the MCUs which are not pre-programmed yet. I will fix that in a moment. But now, okay, let's do it next. So you will see it in action. And then, but I want, we need also some mapping. So the map function will be get pixel or map no, void int. That will be the, then we have a data. Oh. Oops. Oi, 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 oi. Data 32 times 16, or let's say pixels, cells, and then this is also 3. Then we have map pixel, which will map basically the index to the, okay, bye bye Jordi, you will miss the fun, but you can always rewatch. Our map map address to xy, address to xy. So we have int L2, int L0, L1, or L1, L0, and this way. Map address, and then we have different way around. Oh, yeah. All right, let's do that. Pix index. Yeah. So we have something like, oh wait, no. It's actually 32 by 16 in a different way, but all right. So if L0 is greater than, we start what was the first pixel? Was it on the upper one or the lower one? Hey Chubai. Since I am French, I don't talk much in the chat. I like, if possible, talk here about small project I recently completed. Would you give me a permission to share a link? This could be useful. Okay, yes, sure. Share a link. I hope it doesn't get filtered. Potential. Let me check. What's this about? Oh, your PCB 3D printed. Upload your Gerber files. Get 3D printable file in seconds. That's cool. Yeah, actually, but how do you set? Do you generate STL file or do you generate G code with that? Preview, adjust STL. Oh yeah, STL. All right. Yeah, that's cool. I mean, if you have like a small nozzle, I think I have 0.2 millimeters, 3MF. So, yeah, that's cool. Cool project, people. Check it out. Stenchill. Cool name. .com. Looks quite interesting. Okay. So, oh, no, not now. Sorry, I'm really concentrating right now. People can check it out. I really we can test it. Oh yeah, all right. So if L0 is smaller than we have, then we add, let's say y is equal 0, and then we do like a stupid calculation without a lot of int. Okay, this is int y equals 1 otherwise, and then we do x. Oh yeah, if a calculation is because it's going this way around, we need to do x equals L0, and then we have else, or this is basically L1 times 2, and then we have else, which is plus 1. X equals no 32 no 16 30 31 minus L0. I guess this is how it's calculated, and then return x times, oh no, wait, I think we are, yeah, we are messing here with x and y. Okay, let's do this. X times y times 32 plus x. This will be a mess. Okay. So what we do, enable CS, we will get a map here. So this is we should also row and call, we should rename it, because in that case we have call, that's that, and row call, let's do RGB equals pixels map this, and then we will do RGB 0 1 2. Okay, and now we need to do init plasma here. R isn't needed anymore, I guess. Init, oh yeah, no, we need R. Or it will be T, and that's an int. We don't need it to be static. Init plus do we include this? No. Okay, so we have init plasma, then we will do plasma and then calculated pixels, and then do T plus plus. We don't need any R here, we don't need any R here, we don't need the old delays. This is old crap. Where are the pixels? Oh, yeah, that doesn't work. Okay, let's do that. No, how do I do that? No worries, it's a cool project. How do I pass an array pointer to an array with the definition of that is oh wait, it's no, it is like we need like to have this fixed tree in the declaration, but we get gray values anyways, so maybe we don't need that at all here. Let's forget about RGB here and do only this. Yeah, it's like it was stupid. Yeah, that as well. 255 minus we could use also integers here or d words. Yeah, no, times 3. needed. All right. Okay, let's find out before you go to bed, DFGA. Let's find out if the plasma works. Here. Yeah. Oh, our addressing doesn't work properly. It works only for but I can see a sinus plasma, but only for the first half of that. Oh, let me turn down. Oh wait, we have ISO auto. Let's do it. I like it Picasso. Yeah. Wait, let me do shutter. Oh, it's so weird. The blue is so dominant. I have no clue if that. But I have something wrong in the mapping though. It needs. Okay. So we have actually what we have 16 by 32. Let's fix it. 16 by 32. Yeah, I couldn't tell if it's correct. Yeah, there was like a moving blob, but I couldn't tell if the interlacing or the interlacing is working properly. Foo! No, you're not late. You're just right for the good part. Less talking, more making here. Yeah, it's a. I need a better animation there, or just stream. Oh, that was the blob. Pixels y times 32. Yeah, that's how it. And then there is the plasma, which calculates x is 16, 32, which will be weird, but I believe. Oh no, x times. No, wait. Y times 16. Sorry, you're not seeing that, but I'm only fixing stuff. Let's try to program it. Okay, it finished. It's still not working. Hey, what is wrong here? Okay, let me check again. I'm adding. Oh yeah, I think I'm looking it up the wrong way. Row. Oh. L1. No. Y times 16 plus x. This is the last arrow, hopefully. Yeah, not really. If you exceeding the array, there are only, come on, there are only 16 rows and your 16 columns, and you have yeah, you will see. Yeah, here you go. All right, now we need to fix the firmware on those things. Oh no, I'm still recording everything. Okay, let me record that. Yeah, the plasma you can't really make out. Let's do some green. The red isn't very prominent on camera. Or we defocus. I can't tell if this is good night. Yeah, there's like still the blue is so prominent. Okay, we do value by 1. Let me try one thing. No, you're not the, no. If you multiply 32 by 32, you exceed the 512. That's why it needs to be times 16. You skip like the stride is not 32. The stride is 16. So you have like a overflow. You're reading memory after the array. You all are wrong. I know it's late, and your brain, you didn't have like a Schokohase. One blue blob, yeah. Okay. Yeah, but this is something about this one here. Look at that. About calculation of the address. If you multiply here, y can get L1 times 2. So that's 31. And if you multiply 31 by 32, you are at 1000 whatever, not, or 900 whatever, not at 511. That's why the stride needs to be 16. This is important here. It's always, I know it's an array of 512. Yeah. I'm doing this for for not 40 years, but 30 plus years. That's why this is a typical basic graphics error or whatever. Wait, now I'm here. If it's bigger than 255, then clip it. 255, else do val. Right. Okay. That's why I want to clip that and make it less blue. Yeah, artificial light. Yeah. Here we go. Less blue. Oh. Now it's weird. Plasma from hell. It's something in the middle, I believe. I think I'm still wrong with my addressing. Okay, let me fix my addressing first because I see some interlacing here. I think my calculation is wrong. Let me fill it um, with basic data, which is oh wait, yeah. Dead pixels are not programmed MCUs because my jig wasn't perfect yet. But now it's perfect, so we can reprogram them just as soon as I finish it. Okay, let's do RGB is basically, so I know what we are doing. I will do row times 32 plus call. No, I will do it here. No, we had it here before. This was, sorry, this was the row, maybe I should just clone that. Yeah, let me find out like with the addressing. So we had it before, but I didn't do it right this time. Row left 4 and call left 3. Okay, let's try again, and then we will have a static image that I can figure out the addressing. Okay. So red is increasing in this direction. That's what I would expect. And blue, oh, I got it wrong. Okay, we can see it here. Basically, whoa, this is very dark. Let me, no, wrong. Memory card full. I've recorded some shit for hours. Damn it. We begin at the right side and then go round robin, and this is maximum brightness, I believe. Is it though? Which one is brighter, this one or this one? I can't tell. I can't tell if this is brighter than this one. It doesn't look to me like that. I think they both might be inverted. Okay, so let me do the following. Yeah, I know, but the stream, like it doesn't represent it correctly, and these are red here, these two. This one here and this one. I think this one is in reality, I couldn't even tell. It's maxing out. It's maxing out on. Oh, you know what? I will. That brightness is way too high. I will just use lower brightness without any. Oh, and I should just remove row at all. We don't need that because I know that. Let's do this. We just need blue. Oh, yeah. Cool. That should be alright. Oh, wait. Okay. Still can't tell. Which one of those is bright? I still can't tell. Oh. Okay. Minus 16. And then we will see. Okay. Okay, now it's clear. So both start at this side and increase into the other direction. Okay. So I got it now. The addressing is as follows. We have y is L1 times 2. If it's, then we have increment, and this is 15 minus L0. And then we have 31 minus L0. Okay, this is now correct. And then it's that. Okay, now it's fixed. And we can do that. I don't think we will manage to do streaming though on this. Maybe I will add a new. I will do an extra stream for that, but you will be surprised. The end. I would need like to have one programmed. Yeah. All right. This is now the plasma. Yeah. Whoop, whoop, whoop. Now let's fix that. Lava lamp, yes. Okay, let's program it, I guess. And I need to delete TV output in progress, yeah. Okay, I need to delete the file that's too big. Oh, there is not much that I actually stored. 6 minutes, okay. I guess the card is full. Let me check if I have another one that's not full. Alright, I don't need to record everything here. Ah! Huh? Okay, sorry. Yeah. Here's your autofocus. I will move that data a little bit. I hope I don't stall everything. Aye. Oh yeah, I'm recording in 10 bits. That might be an issue, yeah. And my hard drive is also full. Damn it. Let me at least move some of the data here. Okay. Moving data. Now we will take this and yeah, let me turn it off. We have a temperature of 43, which is alright. It seems that this, oh, everything is entangled here. We don't need this programming interface, we don't need this one. Oops, crotch cam. I move this over. And I move view over. Oh. Move view over. Ah! Sorry. Okay, ISO auto. Okay, let's check which row was problematic. I need to heighten that. Let's get some space. Okay, let's see. I will note the rows that were where we need to fix it. I guess it's 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 5. 5, 6, 7, 9, 10, 11, 12, 12, 13, 13, 14, 15, and 16. Okay. 16. All right. So turn it off again. Oops. Okay. Let's place it. I'll fix it so it won't shake too much. It's also standing off. It's not like super perfect. Here. I guess the jig could be a little bit better, so more like retention or something. Here in the center I have like a little bit of a bow. Let's get this a little bit secured. Hope it doesn't. Alright. Yeah, clamps or. But then I need to be sure that. Okay. How much space is it? I don't want to scratch the PCB. It could be slightly higher, maybe. Too high. That's 0.5 millimeter movement. And I need to move it slightly in this direction. I think this is good. So, row 1 and 2 were alright. This is row 3, but this is not like a perfect column. So we have this is 2. This is 3. I have all the increments, and now I will run the programming code. Here you go. And see what happens. Nope. Okay, it adjusts. Still not. No contact. Am I even correct here? No. Oh yeah, it can't. Ah, damn it. Because the power is off. Okay. Let me move it over. I should power it on though. Okay, I have my proper increments here. Yeah. Okay, now let's power it on again. I guess it will light up. Yeah, it's lit underneath it. Okay, now let's start again. Nope. Okay, let's see if it adjusts. Huh? Am I off? Oh! There is another issue. When the JTAG isn't connected to USB, there is no connection. Okay. Okay, we're almost there, peeps. We're almost there. All right. Okay, let's start over again. Embarrassing. Okay, let's start. And here we go. Still. No, still didn't connect. Am I so much off? Huh? We are not progressing. I don't know what the issue is right now. Am I right here? We try that. If I'm on the right side. No. It's not connecting. Okay. I guess I need to. Okay. Let me pause that for a minute. And see if I can get anything programmed while yeah, this was okay. Let me check if we have a connection to the programmer. Where is it? Here. Oh. Huh? Oh, don't tell me we have like the wrong driver again. Oh, come on. Somehow, let me check that. Leap USB. It installs it by default to Leap USB. I don't know why. That's why it's not working. Okay, uninstall. And we have even the driver programmer here. I had that before. I don't know why it's happening. Okay. Let's see if now. Okay, now. Yeah, and we get the address. Oh, yeah. By the way, this is what I meant before. Address, there is like no UID. It's like 70 and then 0000000. There's no actual UID. Okay, weird. I don't know why. Why this. Okay, I think this is now. Now we need to go back to the start position here. And let's start over again. If I have to do it every single time, I need to Zedic again? I don't know. Okay, let's start. Flash successful. Here we go. Oh. This one tries to adjust. Here we go, successful. It moves on. Oh, this is the first time I'm seeing that in action, the correction code. Nice. Nice. That's cool. Oops. Sorry. Here we go. Here, green, green. You can also see the G codes. The offset of each MCU is 5.4 millimeters. Cool. And that's it. It will move in that direction and then return because it's in the inner loop. Okay, that was row number 3. Now we need to go 2 more. I would need like a perfect indexing, which one doesn't work or whatever I want to do. Okay, 1, 2, 1, 2, and then yeah, the rows, but this is only half the row, so we would need to run it several more times. This will take a while. If it moves right to the next, it was successful. That's really cool. Okay, 3. We have 1 check mark. We need a second one there, most probably. You know what? I can find out. Yes, that's true. But that's also quite helpful if I have like a slight shift and the correction is just summing up. Although it might be a problem in the end for the first one because it's not reverting that when I move back. One thing that I might want to change, so this was 5. If I don't want to run it for every single row, I could check in which rows it actually happened, because we have like the upper and lower rows, and we are doing only the upper rows. Okay, let me check upper row. We also need to move to the next one, I believe. So this is 6 and we move up. And then let me check. And this is really not necessary, but well, now I have the sticky tape right there where the head is. Yeah, this is 1, 2. That's the lower one. Yeah, that's the lower one. We need to only to fix the upper one. So I will check exactly which upper and lower ones we want. I just okay. So we have 6. 1, 2, 3, 4, 5. 6. Yeah, we need the upper and the lower. So upper, lower. We don't need the upper, so only lower on 7. 8 is alright. We need upper and lower on 9. Upper and lower. We need only lower on 10. 11, 12 is only lower. Yeah, that was upper, lower on 13. 13, upper, lower. Uh, 14, also upper, lower. Oh, interesting. I see an LED bug here. Look at that, the red isn't working. That might be actually the hardware issue. So the 15 is 16, 14, 15 is both upper and lower. Okay. Yeah, I might need to fix some LEDs at some point if there is like a. I'm wondering if that's a reflow issue or if the LED is broken. Okay, so we are at the upper ones. Yeah. We are doing upper ones, so let's lower that and continue with the programmer because we need on 6 we need also both. Isn't that cool? And this is how I planned it out when I designed this PCB. So it's actually working. Nur, yeah. Only the one issue is that I have like some the pins are inverted in the different rows. Oh, there are 2 LEDs which are JTAG pins. I deliberately leave them off. Right now they stay red because if I change them, I will be only able to reprogram it using power cycling, which I don't want to do right now. So 6, now we will continue with 9. So we're going 1, 2, 3, 4. This is 9. Now we continue with 9. And yeah, the ones that are completely off, these is what we're trying to fix now. Okay, there will be 13, 14, 15 will be also. We are 9. 10 and 12 are only the lower ones. 13. Oh, we will draw more power. I need to be careful. Yeah, it's already dropping to 2.6 volt. Yeah, we are already at 4.5 amps because we have new MCUs working. It dropped to 2.6 volts, which is quite low, but they're still programming. Uh-oh. That doesn't work anymore. Now it flashed successfully. Cool. Okay, now move on. 10, 11, 12. Oh no, that's the wrong direction. Okay. Yeah, wrong. That's 12, 13, and this is where we continue. When I start like with a new board, I will do a complete board like also with Y array or a Y loop, not only X. So I can actually get a coffee. Here you go. Uh-oh. 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 Yeah. It found the offset. I mean, what is the imprecision that we can get? And not more than 2 point. Uh-oh. Here we go. And also, the pogo pins are also not perfect. So we need to take that into account. The board shifts quite a lot here. Okay, that was 13, 14, and 15 are also needed. Okay, run. Now that the boards are getting hotter, they draw more current, I believe. Maybe I should just turn off the LEDs. Can just unplug those. Uh-oh. 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 Woof. I redo like the full row, but only one row, like not okay. And one more. Yeah, I'm not searching for the explicit MCU. I could do it. But then I would like really need to find out which one it is. And I rather wait. Oh. It didn't register my last movement. Okay. Yeah. I believe it's a little bit low. I mean high. I guess I can give it a slight push downwards. I don't believe we will be able to stream today. But we will see a full array working, except for the last LED. We can take a look at the LED underneath the microscope to see what is the issue. Why red isn't working. Might be just a reflow thing. But how do we rework that? I mean, we can use our fine soldering iron to do it. Okay, now it's better. When it's lower, it's better. Boop! Boop! We are already tomorrow. I know! Okay, let's check if we got all the not worky ones. From the upper, this one was, blue is working. Okay, this is working, this is working, this is working, 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 working. Okay, now we will change the lanes. Change the lanes, we can stick that down here. That also, because I know. Camera is a little bit off here. Do you want a close-up? I give you a close-up if you like some porn. Programming porn. Okay, so we lower it, then 16 was all right. We move it one row down, this is the first LED, and then we switch this pin here, and that's it. Now we can start all at once. I don't believe. Had issues with that already. Okay, let's see. Yes, that works. Okay. Yeah, that's a heat bed. We can print on that right away. It's like the print beds at the beginning of the RipRap times. PCB heating bed. Here we go. Should we check the temperature? Okay, how much is it drawing? 4.5 amps, 3 volts. 43. Yeah, it's bending. Okay, so this is 15. 15 is done. Was the last pin? Whoop. 15 is done. Then we move to 14. What do you mean? Yeah. It's hand warm. Like fever. Slight fever. It's running the plasma while it's programming it. Chupa, yeah. Bye bye. See you maybe next week. Oh, it had a correction here. Cool. Uh-oh. No. Uh-oh. If it doesn't manage to program it, it did. Okay. Woo! Ah. Maybe I will do like an final step where it's doing it lowered and then moves around to basically scratch off some, but this is ENIC, so that shouldn't be oxidized. The LEDs are running at 2 amps max. Since this is now red or blue, it's maximum like 1.2 or 1.3 amps. Milliamps. Sorry. That's not really per MCU, so not that much. Okay, next row is 13. This is row 13. That will be a lot because there is a lot going on in row 13, I believe. I will check the power consumption. We are still at no, 1.2 milliamps per LED. No, per red is 1.2. I think blue will be 0.5 more or less. Deny. This is some spam. Yeah, I need to clamp it down or fix my frame. No, Fu. I have to do it one more time. Once. Uh-oh. once I have the firmware that you can flash over SPI. But I want, for the showcase for today, I want to have all the LEDs working. So we are at 12, I believe. Uh-oh. Oh, are we so far off? No. Here we go. New offset, but the board is moving up a lot. I hate it. Some sort of clamping mechanism would be nice. There will be, in total, it will be 128. I know it will be challenging. Yes, wagon loads. That's what we are flashing, the ones that we missed before. Okay, that was row 12. Now right now we have only this one, which is fixed with bodging, and as soon as the next assembly is done, we have 19 in total, but I will use 16 for the video. That's the goal for the next video, which will be one 8K MCUs. Oh, I hope I'm at 10 right now. No clue. Might be the wrong row. Okay. That's 11. Oh no, I'm fixing a good row. That didn't need fixing. Should concentrate. Yeah, that's what was suggested before, but that works. I don't know what you. We have like perfect offsets and correction. Okay. I just need some tool to address it correctly. If I have like wrong programming, I could basically prompt it and find out, like, get a list. So there's so much I can do with code. As soon as I have like the upper levels working, I can fetch the data. Oh, this controller isn't responding, and this can be translated into a physical coordinate, and the printer could be addressed with that. Like the Python code, I can just feed it with MCU ID and position and program it. So that's all possible, but that all needs programming and some code. And in the end, I guess it scales. But okay, where are we at? Now I'm just talking too much and not concentrating. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We programmed 10. We need 9 and then 7. Okay. Oh, I think I'm scratching the surface, yeah. Okay. There you go. Also dangerous to scratch off the solder mask because there are some power lines and I have a ground pin on that Pogo programmer. At least there are no 12 volts anywhere. Okay, we had 10, this is 9. Let's make sure. 1, 2, 3, 1, 2, 3. 1, 2, 3, yeah. We are at 4.66 amps. Yes. Okay, that was 9. Now we need 7. Okay, 7. Let's start. I'm wondering how long the Pogo pins will last. At some point they're not sharp anymore. I took the pointy ones, but I should maybe have used the different ones. I have like a assortment of different Pogo pins. Okay, that's 7. We need only 3 more rows after this one. Then we have a full working array. Oh wow, there's some spam going on Twitch. Some more full screen programming porn. Everything bends. Okay, now 6. We are almost at full set and 4.69 amps in total right now. Power consumption. That's powered from USB power delivery. It's only 15 watts though. Yeah, 14 watts. It's exactly what I calculated, which is really cool. Or extrapolated, because the maximum rating would be more like 6 amps is the absolute maximum rating, but we didn't reach that in our test. Hey KZ Mans, or Kzmans. It's programming individual MCUs with our base code, test code. We have missed a few MCUs before. We need only to fix 2 more rows to test again, to turn it around and see how it works. We have a basic plasma going on that thing. I'm wondering if I can set up a faster transmission speed for the OpenOCD transmission, because that takes quite a long time. And yeah, oh, you can see the light already underneath. A few? You mean like missed MCUs? Yeah, it was a lot more than that. It was like 30 missed ones. The upper rows we have missed like 16 and one almost like a complete row. There was no correction for the programming. Now we have correction, and that's cool. Okay, we need only row 3 after that, and then we are done. I hope. And there is this broken LED, which I guess with 512 LEDs, that one is like faulty. Might be like, yeah, still a good yield. That's 0.2%. If it's a faulty LED, I mean, it could be just the PNP here. Is it still hovering? Yes. All right. Okay. Last row to program, and then we can run it in full glory at 4.7 amps. You. Okay, let's zoom out. By the way, it's a 3D printer, if you didn't notice. And the board is fully powered. I'll eat some chocolate. I also suspected. Okay. Last 2 MCUs here. Let's move it up a little bit. And let's see it. Tape. The tape didn't do anything. Oh! What is that? We missed 1 row. Okay, these are the JTAG ones. They don't work, but this row is missing. We missed 1. Which one is it? 1, 2, 3, 4, 5, 6, 7, 9, 10. Oh no. We did 11 but not 10. Alright. 1 last try. Wait, was it upper or lower? Lower. 10 and the lower thing. Okay. Yeah. check. Two more. Yeah. How did I miss this row? Yeah. Imagine it can coordinate it live by testing the MCUs and trying to address them. Like the MCU can read basically which ones are addressable and have the right version and then navigate to it and fix it. All right. Okay, now did we get it? Now we got it. Okay, these are only the JTAG pins that are. That's cool. All right, peeps. Let's take a look at the broken LED here under the microscope, and yoo-hoo! Okay, let me turn off autofocus. And let's defocus a little bit. Yeah, here we go. Don't mind the two JTAG pins. they will work after all at some point. Oh, wait a second. One of those isn't programmed. It should be, they should be all red. So I guess I need, but this I will do another time. I need to reprogram them anyways. Let's take a look at the broken LEDs. Like the one in the upper left corner, which only displays blue. Oh, it doesn't even display blue anymore. Maybe the power drops. No. Oh, interesting. Let me test if I can increase the voltage. If it's not getting enough power, it might affect the blue actually. 3.1. Current limiting? No. Okay, when I touch it, I guess it's not reflowed correctly. Okay, let's figure it out underneath the microscope. Yoo-hoo! Let's go! Oh, I turned off the camera. Yeah, I guess it's the stream is coming to an end. Let's take a look. Bad reflow? Yeah. Okay. Yeah, totally. Wait. Let me check. Okay, let me get the tweezers and let me get some extra light here. I won't be... Oh, yeah. Look at that. Oh, it's coming off completely. Yeah, this is... This LED is no good. It came off. Okay, I guess I could try to reflow it, but I need to turn off the power. We can't do it like that. I have this little soldering iron and I have some... Okay, so let's turn off the power. Let's turn on the soldering iron. Okay. Okay. Now it's sharp for me as well, not only for you. How do I put... Okay. I'll give it some... This is 1 millimeter LED, huh? Yeah, this is the correct way here. Yeah. Oh. Oh. Where is the power coming? Okay, let me disconnect it completely because we are seeing some... Huh? There is no ground! So weird. Hope we don't break it. I guess I can't reflow it like that. It's... Yeah, it's pulsing. No, it's coming off completely. Oh, wait a second. The pads came off. Alright, that's the issue. Okay, this is broken. I don't know, maybe I bumped it at some point. I might have bumped it at some point because that's in the corner. That's what typically happens. This is the first time I noticed that this LED is only working blue. So let me clean that up. And let's get a new LED because I have a plenty of those here. Yoo! Ah. Yeah, I'm just using the pump. Shit, I dropped it. I'm wondering how many of those I will repair. I probably won't repair any more than this one because yeah, that doesn't scale. Now we need to check the orientation of this one here. I guess this way around. Is this correct? We check. Power is this is powers. This is power. The power pin is this one. Yeah, that's correct. How do I solder that? I need more solder though. This won't work if I don't have plenty of solder. Yeah, not really want to reheat this whole thing. Let me try to get it like that. I'm anxious that I will I will destroy it because it has so many ground planes. My hopes are that with the help of surface tension and enough solder, maybe. Oh no, I need a knife. Do I? Not sure if, no, the knife is too big. Yeah, this tip is destroyed already. Look at that. Wow, okay. Let me get a new tip. Here we go. Wait, I have a conic? No, here. Oh shoot. The wrong thing. I have a small knife. think it should be somewhere here. Yeah, but it's not so small. Okay, this tip should be better at this. Yeah, that, I guess that worked. I need to be really careful. I have only one extra set or something. Don't really want to work with a conical one. I mean, this is not much better than a conical tip, but issue is that this power pin here might take a lot of heat. Oops. Okay, let's turn it. This is 350. This is already at its limit. For the LED, I don't want to melt it. Okay, let's turn it on and see what happens if I got all the pins. Not sure if I got green though. I can test that. Okay, we have red and we have blue. Okay, that should should be good enough. It's gross, it's looking gross, it is gross, but it's working, okay? We fixed that with our resoldering, reworking facilities here. Okay, I will get some IPA here to clean that up. Imagine you're not capable of doing that. You're only ordering like boards that are finished and don't have the tools. I mean, this is, look at how big the Q-tip is here. I can't reach even like these corners. How do I do it? Titanium is conductive. I don't really want to mess around too much with this gross. Okay, nobody will notice. That's cool enough here. Boop boop. This is so small, you wouldn't even see it in real life. Look at that. Wee wee. Now we are fixed. Woohoo! Streaming. Next time it will be streaming. Okay, you know what? I reconnect the thing. You can watch it because it's beautiful with this power. Reconnect to clean it? Yeah, no, not doing that. I'm a YOLO guy. Whoop. And maybe I can I'm at ISO Auto. Let's fix that. Okay, I need to find to program the. Oh, by the way, the power boards will arrive probably this week. So we will do more of the power handling with reflowing and making the power boards. As it looks right now, I only need for 16. I need only 4 power boards. Do I? Yes. 4 of the planned 40. More amps. Yes. Cool. All right, peeps. Thank you for joining the stream. It was a blast. We had a nice, what is it, 5 hours? What? Yeah, talking 1.5 hours and explaining, but it works. And I'm surprised that we are able to achieve like 16 megabits. It's pulling right now. Oh, there is no LED on this one. I didn't put one there. I was like, it was too tight, and I have so many lanes here. There are so many like CS lanes in the lower right corner. For, if you mean that, it's pulling right now 4.86 amps, 15.5 watts. A little heater. 15-watt heater. Yeah, it wouldn't even keep your coffee hot. Anyways, thank you everyone. I see you next time. Bye bye. And thanks for the input and likes and for the subs and everything. Good night.